Please join me in welcoming the ICESat team working on measuring environmental changes with Altimetry.
My name is Dallas Ballantyne. I'm from Minnesota. I'm a rising junior.
My name is Nikita Barati, and I'm a rising senior from Arizona.
Hi, my name's Karan Basine. I'm a rising senior from California.
Hi, I'm Eric Dahlman. I'm a rising senior from Kansas.
Hi, I'm Cody Garcia. I'm a rising junior from California.
Hi, I'm Paul San Giorgio. I'm a rising junior from New York.
Hi, I'm Jason Wren. I'm a rising junior from Texas, and our mentor was Dr. Timothy Urban.
So our mission background is that ICESat stands for Ice, Cloud, and Land Elevation Satellite. ICESat 1 and 2 are NASA satellite missions with the objective of measuring ice sheet mass, balance, and elevation, land topography, vegetation characteristics, and cloud aerosol heights. ICESat 1 was launched on January 12, 2003, and was in orbit until 2010. ICESat 2 was launched on September 15, 2018. ICESat 1 and ICESat 2 were launched on the Delta II launch vehicle from Vandenberg Air Force Base in California. ICESat 1 was deactivated on August 4, 2010, and re-entered the atmosphere on August 30th. The ICESat 1 orbit altitude was 600 kilometers, about 373 miles, in frozen orbit, meaning it will remain fixed essentially at the North Pole. Its velocity was about 15,434 miles per hour. It had a 3-year lifetime with a goal of 5 years use.
The NASA GLAS, or Geoscience Laser Altimeter System, on the ICESat mission had the primary goal of observing the polar ice caps and their impact on global sea level. The GLAS instrument operates with infrared and visible laser lights that eye-safe signals. The laser light pulses illuminate the Earth, enable it to measure the surface elevation of the polar ice sheets, topography, clouds, and aerosols with extreme accuracy. It measured the vertical distance from orbit to the Earth's surface 40 times a second, while traveling at 26,000 kilometers, or 16,000 miles per hour. Between ICESat 1 and ICESat 2, there was NASA's Operation Ice Bridge, where airplanes equipped with scientific instruments flew over the Arctic and the Antarctic. ICESat 2 is equipped with an instrument called ATLAS, or the Advanced Topographic Laser Altimeter System, which has a laser that can emit 10,000 pulses per second. ATLAS has 3 main tasks: to send pulses of laser light to the ground while determining where the laser is pointing, to collect the returning photons into a telescope, and then to record the photon travel time. The ICESat 2 spacecraft orbits Earth at 15,660 miles per hour and an altitude of 310 miles. Every 91 days, it completes 1,387 unique orbits. The mission collects a terabyte of data daily.
Mechanisms on board the satellite measure the round trip of laser photons as they depart from the satellite, reflect off the ground, and return to the receiver telescope. By matching those times with the satellite's location in space, the heights of Earth's surface can be determined. According to NASA, ICESat 2 will measure how much melting ice sheets in Greenland and Antarctica contribute to sea level changes, measure how ice sheets, glaciers, and more are gaining and losing masses in different regions to help researchers understand the mechanisms behind those changes. 3, to estimate the thickness of sea ice and monitor any changes. 4, and to measure the height of forests to calculate the amount of vegetation in a region.
For our project tasks, we used the training we received with Python coding from Lesson 2, and we aim to analyze the data from the ICESat missions by plotting land topography, roughness, and slope on graphs and present the data in a video less than 20 minutes in length. We chose the White Sands area because it is a primary calibration site for ICESat 1. This site was chosen for its geophysical qualities, including its flatness and reflectivity, and it was also chosen for logistical reasons, as it is a domestic and secure site. Calculating slope and roughness values are important in that they help infer material properties of the surface being analyzed, and these factors may also have a topographic influence on waveform return.
Our main approach to our project task was to create Python code that will be used to read and plot data. We used data from 3 sources: a DEM, or digital elevation model made from data from 2 aircraft LiDAR missions, ICESat 1 and ICESat 2. Using DEM data from 2003 and 2007, aircraft missions, which include latitude, longitude, and elevation values, we plotted 2-dimensional and 3-dimensional topographic maps. We also used color bars to illustrate the differences in elevation. We then divided the map into grids and calculated slope and roughness within each grid. Roughness was created as a standard deviation of the elevation in each grid, while slope was calculated using a least square fit, which created a 2-dimensional plane that best represents the 3-dimensional scatter plot. The ICESat-1 data included 20 campaigns, or approximately months of data collection, with a time span from 2003 to 2009. This data differs from the DEM data, considering that the ICESat-1 satellite collected tracks of data, not entire planes of data. These data files included all the parameters given in the DEM data, but also included skewness and kurtosis values. Skewness is the measure of how off the distribution of data is from the normal bell curve, and kurtosis is the measure of how sharp the peak of the distribution curve is. This allowed us to not only create graphs showing our calculated slope versus latitude and calculated roughness versus latitude, but also slope versus skewness, kurtosis versus roughness, and skewness versus latitude.
Since the ICESat-1 data is collected linearly, unlike the DEM planar data, dividing up the data was different as well. The data was divided into 7-point segments or groups of 7 data points instead of 1-kilometer grids. The roughness for each segment was calculated the same as the DEM data by computing the standard deviation of the elevations. However, the slope was calculated differently, creating a line of best fit using the 7 data values in each segment and getting the slope of that line. The ICESat-2 data were taken from the NSIDC, or National Snow and Ice Data Center, database and included data from 2020 only. ICESat-2 differs from both ICESat-1 and DEM as it has 6 lasers which create 6 distinct tracks of data. The data was also stored in an unfamiliar format to us, which was HDF5 files. Because of this, one hurdle we had to overcome was learning to navigate and read this file type. NSIDC provided example Python code which allowed us to figure out how to navigate this kind of file. Inside the HDF5 file, there were many sub-branches with their own data path names. These sub-branches included the 6 lasers, which each had their own elevation, latitude, and longitude data.
Given that we wanted only the data of white sands, the complete dataset had to be filtered as the ICESat-2 track went through much of North America. This was done by only using data that was within the latitude and longitude coordinates of white sands. We then used what we had learned from the NSIDC example code and from the C's Python Basecamp to take the filtered latitude, longitude, and elevation data from each laser and create plots of them. Because each data point was 100 meters apart, every kilometer of data was represented by 10 data points. The slope in meters over 1 kilometer was calculated using the curve fit method from the SciPy package. The roughness was just the standard deviation of a kilometer of data, and the slope in degrees was calculated by taking the arctangent of the slope in meters. These trends were then also plotted against latitude and longitude.
This video zooms in on white sands using Google Earth, showing the real location that these missions had studied.
Here we show the 3-dimensional DEM plots of latitude versus longitude with elevation as the z-axis, which were used to visualize the white sands topography in the years 2003 and 2007. These next 2 plots are 2-dimensional DEM plots. As shown, the points in the scatter plot are grouped into grids which are 1 kilometer by 1 kilometer in dimensions, and these grouping of the points were used to calculate slope and roughness within each grid. This last graph for the DEM data is of slope versus latitude, where the median latitude from each grid was plotted, and it demonstrates the flatness of white sands from the airborne survey data. This plot shows data from the 6 ICESat-2 tracks on the same plot as the 2 DEM maps together. And this map allows us to see which of the ICESat-2 tracks overlapped with the DEM data in terms of longitude and latitude coordinates.
These 2 plots show the average kurtosis values per segment and average skewness values per segment versus the median latitude per segment. This shows data of just one track, L3J0137, of the many ICESat-1 tracks we plotted. As you might notice by looking at the plot, it seems that kurtosis and skewness both spike at approximately the same latitudes. This suggests that kurtosis and skewness values are closely related and that those latitude points of the white sands might be less flat than the rest of the latitudes measured. These two plots show average kurtosis values versus the roughness per segment and the average skewness and versus the slope per segment. This is the data from track L3K1307. For the roughness versus kurtosis plot, there is a trend showing that the higher the kurtosis, the lower the roughness. This suggests that over rougher surfaces, the effective footprint is larger than when it is not as rough. We can conclude that since roughness and kurtosis are opposites, it would make sense that as one increases, the other decreases. For the slope versus skewness plot, as the skewness increases, the slope gets further and further away from zero. We have not come to the conclusion on why the plot has this trend. However, as our future work, we plan to take a closer look of the correlation between slope and skewness across all our data.
So for the ICESat-2 data, this first plot shows the 6 ICESat-2 tracks in a 3D coordinate plane. There are actually 6 tracks as pairs of tracks are very close together. The other plot shows the slope in degrees versus latitudes across all 6 tracks. We also plotted roughness versus slope and found that the greater the absolute value of the slope, the greater the roughness. Thus, as slope approaches 0, so too does roughness. Future work would also include comparing the data from the different sources where they overlap.
For our impression of the virtual SEAS internship, there were both highlights and challenges. One highlight includes how we were able to get detailed training in both Earth and space sciences, as well as Python coding, which will be very useful to our careers and our future paths. And we also got to hear from interesting and experienced speakers, scientists, and researchers that had overlapping research and expertise in the fields we were researching in, as well as they gave us new perspectives on different aspects of Earth and space science. And we also got the opportunity to conduct real-world NASA research using satellite data. So with highlights, there were also some challenges. One challenge included efficiently and effectively making the best use of all of our skills. So some people were more experienced in Python, some people were more experienced in the Earth science background. So working together to put our skills together and make the best project possible. And then also communication without meeting in person. So obviously we couldn't meet in person this year, but we were able to utilize platforms such as Zoom and Discord and Basecamp to effectively communicate and get our project done.
So before I was a SEAS intern, I didn't know nothing about coding. I didn't know that much about earth science in general. I was able to gain a better understanding of coding and like how you can use it for like mathematical equations, how it can help make graphs for like science data and stuff from my satellites up in Earth's orbit. This internship has helped me in a way where I am more motivated and get my degree in aerospace engineering or aeronautical engineering, specifically in like spacecraft design and stuff like that.
So before I came to SEAS, I've done research before, but it was more in a lab setting. And I've never really used coding and computational research and applied to research I've done before. So SEAS gave me a new perspective on that and how earth science research and coding can go really well together to make some really impactful results and breakthroughs. So I think definitely the internship taught me a lot more about Python coding and improved my skills in that, and showed me in the future how a lot of jobs I can go into can work really well with the intersection of coding and use it to really make some impactful changes.
So for me, I've taken a few chemistry and physics classes in school, but earth and space science isn't something I'd really been exposed to that much before. So SEAS gave me a lot of resources for that, and I learned a lot. Also, I've had a lot of coding experience before with research too, but I hadn't really had the opportunity to apply it to something like with actual satellite data from NASA. So that was really interesting. And it kind of showed me that with my programming skills, there's a lot more paths than I thought before. Before I kind of it was pretty narrow. I thought you can become a software developer at a tech company, but now I know that the skills I have could also be used for conducting research in NASA, which is pretty cool.
SEAS has contributed to my future education and career plans by showing me how important these NASA satellites are to our everyday lives. This encourages me to want to take an education and career that deals with this type of work we did here and with satellites. Also, the new skills I've gotten in Python opened so many opportunities for me.
This opportunity has helped me decide how I want to work with NASA. I learned how to code in Python. This has jump-started my career with data analysis, and I now have a solid base to jump off of into my college years.
For me, going into this internship, I already had some coding experience working on the robotics team, but I didn't really learn a lot about astronomy, earth science, or data analysis at all. So being able to combine something I'm familiar with and something I'm not was really cool and helped me realize that there are a lot more coding career paths out there, more than just robotics and like a software engineer.
Before I started this internship, I had no idea how much NASA viewed our own Earth as a whole. You always hear about the Apollo missions, the Voyager missions, all those really big ones that go out further into space, but you never hear that much about the ones that observe the Earth as a whole. So that really helped broaden my horizons. NASA isn't just about space, it observes the Earth so much as well because it's part of our solar system. This has helped broaden my horizons very, very much. Learning new Python coding skills is a massive one. Learning about Earth science, meeting so many great team members, getting to view so many speakers and people that work at NASA and working with actual NASA data and scientists was an amazing experience. It just finally helped me choose on my degree, which is aerospace engineering.
So we have a question for the ICESat team. How do you think about scientific data and their analysis and presentation after your SEAS experience?
Yes, so I can start for this question, and then anybody on my team can add on after I'm done if needed. But I would say there's kind of two sides to this. The first one was just the process of data analysis. I think we had these super large data sets with like 40 or 50 different values that were collected from the satellites, and we only really needed like 3. So we would like clean these data sets, extract what we needed, and then go into the process of like applying these mathematical models. So I think we really did realize how important that process is. And it was really cool to be able to have a plot that we could like show to a family member or show to another one of the SEAS teams, and they'd be able to understand it. So that's kind of the first side. It was really interesting how we could go from something that was just this large complex data set to something that was understandable. And I'd say the other thing was understanding the practical applications of this with NASA's work. Our mentor revealed a lot to us about how by like understanding qualities like slope and roughness, it can help to inform future satellite missions because better understanding of how the satellite collects data and in certain scenarios, how the data collection process must be adapted to account for that. Yeah.
So does anybody else like to answer that question? So based on your experience with the SEAS internship, what do you think was your biggest challenge in getting your project completed?
I can answer that one. Oh, Cody, do you want to go?
Go ahead.
Okay. I think basically our biggest challenge was having to adapt to a virtual environment, but we did overcome that because this was a heavily computational project and we utilized different platforms such as, I know our mentor and the rest of our team, we used Discord to communicate with each other. We held our consistent meetings to kind of check on each other's progress. And so we just held each other, I guess, accountable and utilized all our resources virtually in order to overcome that kind of barrier of not being able to meet in person for this internship. So I think though that was a challenge, we were able to overcome it with the resources we utilized.
And I think one more thing just to add on to that, to what Nikita said, like with the actual project was how we would all be working on like different data sets. Like for example, I was working on the DEM data and Jason was working on the, I believe, ICESat 1 data or the ICESat 2 data. So then we would like take some of his tracks and like overlap them with my maps to make sure that we were both analyzing slope and roughness for the same latitude and longitude surfaces so that we could actually compare our different values. So like, I think that was another important part, just making sure that all the different things that our team members were working on, we were connecting and overlapping in the right ways. Yeah.
What did you learn most from doing the research that you didn't know before?
So with this research, we will learn how the lasers from the satellite, it was kind of interesting because Dr. Urban explained it to us, how it had to be very precise and like very specific. so that it bounces back and then it doesn't interfere with all the other radiation that happens in our environment and from the sun. So it amazes me how the satellite with just lasers alone is able to make precise calculations on the slope and roughness and the altitude of various mountain ranges and the ice caps.
Add on to this, Cody. I especially found it very interesting, specifically with the Atlas laser, how it was able to fire one laser at eye-safe signal, so it wouldn't interfere with human data either. Go through, and then it would calculate the distance to go back to the laser. I found that personally very, very interesting in that section of the project. Plus, also, it was really interesting using the NASA EYES programs on our computers for the CEAS Journal internship. That was an experience that was really interesting to get to view the Earth from the perspective of the satellites, where the satellites are rotating around the Earth. That was another really intriguing section of the project.
So I would be interested to hear from each of you about what your plans are for your major in college, and did SEAS affect that in any way?
I can go first on this one. At least for me, I plan at least to major into something to do with like computer science or engineering. And the SEAS program definitely influenced me towards pushing me towards that, because before I've had, like I said, I had programming experience like for robotics and other facets, but like this really showed me how important like data science and programming and how linked those are together, and how much of an impact like I can make in the world by working on this. And so I guess that just helped influence me to push me to want to do something computer science related in college.
For me, the SEAS program showed how NASA uses a lot of different scientists and engineers. I always thought they had to be like aerospace or like computer programmers, but the general education that we got showed how like they need like any type of STEM field you can find a job at NASA there. So it really solidified what I want to do in college, which is like electrical engineering. But I always believed I couldn't do that for NASA, so I was always on the edge because I always wanted to work for NASA. It was always a childhood dream of mine, but it kind of conflicted with what growing up and in high school, all my classes showed me what I love to do, and now I know I can do both in the future, hopefully, for NASA.
Great. Eric or Karen, do you want to add anything to that?
I can a little bit, and then Eric can go after if you'd like. I'm not entirely sure what I want to study actually. I was thinking like, because I'm a senior, I'm going to be starting college in the fall. I was thinking like computer science and economics, and I think either way, it was really important to learn about climate change, because I think that's like one of the biggest, most pressing issues that we face. Like even if I go into a career like revolving around economics, I think it's important to understand how like policies like affect like the amount of emissions and how they have to like correct for environmental externalities. So I think like no matter what, I'm really glad, no matter what I pursue, I'm really glad I got this experience in high school, because I think I was introduced to a world issue, like the one that people all across the world are trying to address at this time. And then I do know that I'll like also want to be in my career using like data science and computer science. I think those are incredibly useful tools. So I think it was great to get some experience learning Python and using mathematical models as well. Yeah.
The SEAS internship definitely helped me choose my degree, which was aerospace engineering. I was definitely thinking about leaning towards that path before the internship, but the internship definitely like, this is really what I want to do. This is actually what I want to do. So it was really interesting. I definitely need to get a different perspective of it, because I always learned about, you know, most popular missions, space history courses. You always learned about the most popular ones, but they never really covered any of the ones they covered in the SEAS internship. So it was nice to get a broader range of information and different satellites that I never learned about before. And that definitely pushed me into my career path. So hopefully maybe working for NASA or maybe in the private sector one day.